In this unit, we've been studying in depth two new categories of functions, polynomial functions and rational functions. Consistently, a key component of any graph is always the graph's x-intercepts. Graphically speaking, x-intercepts are spots where we touch or cross the x-axis, but algebraically speaking, x-intercepts come from zeros, in other words, numbers that make our function equal to 0. So to find our x-intercepts, we set our function equal to 0 and solve for x. As we've seen, sometimes this is fairly easy to do, and other times it's substantially more complicated. However, regardless of what it takes to get there, once we solve for x, we've now found all the places where our graph intersects the x-axis. Let's think a little more about what this means. Once we solve f of x equals 0 and find our zeros, or our x-intercepts, we found the only places where we can intersect with the x-axis. So at any other point on the graph, we have to be either above or below the x-axis. And if we take it one step further, it also means that between two intercepts, all points are above or all points are below. There's no way we can be partially above and partially below if we're between two intercepts and there isn't an intercept between them. One way to determine which situation we're in at any given point is to find the function's end behavior and see how it coincides with the intercepts. As long as we determine both components accurately, they will come together harmoniously, and all the behavior on either side of the x-intercepts will flow smoothly. In this section, we're going to look at another way to determine where our non-intersecting points lie on our graph. If f of x equals 0 gives us x values that represent intercepts, then what we really want to know is which x values have outputs less than 0 and which x values have outputs greater than 0. Instead of solving an equation, we're going to solve inequalities. Let's start with polynomial inequalities. If f of x is a polynomial function, then a polynomial inequality is an inequality taking on one of four possible forms. F of x is less than 0, f of x is less than or equal to 0, f of x is greater than 0, or f of x is greater than or equal to 0. So if we're solving an inequality of one of these four types, essentially what we're doing is, like with our x-intercept problem, we're looking for the x values that make this statement true. So instead of looking for x values that give us an output that's strictly equal to 0, now we're looking for x values that give us a value that's greater than 0 or less than 0, depending on which inequality situation we're in. Our most basic situation is when f of x is given by a graph. In this case, all we need to do is determine which intervals of the domain satisfy the inequality. So graphically speaking, anytime f of x is greater than 0, we're above the x-axis. Anytime f of x is less than 0, we're below the x-axis. So we're trying to determine which x values correspond to outputs above and below the x-axis. Let's look at an example. So we want to solve each polynomial inequality given a graph of our polynomial function. So here's our graph, and we want to solve each of the four possible polynomial inequalities: f of x greater than or equal to 0, greater than 0, less than or equal to 0, and strictly less than 0. So before we dive in, let's think a little bit more about what this graph is telling us. So as we know, anytime we're on the x-axis, we've specifically hit an x-intercept. And in order to solve algebraically for those specific points, we're solving the equation f of x is equal to 0. So in order to determine any point where we cross the x-axis, we set our polynomial function equal to 0 and we solve for x. So in this case, we have four x-intercepts: -2, -1, +1, and +2. So these are the specific outputs we would get if we set our function equal to 0 and then solved for x. Any point above the x-axis solves the inequality f of x is greater than 0. So the polynomial doesn't change, but now instead of solving an equation, we're solving an inequality. So any x value that has an output above the x-axis solves the equation, or excuse me, the inequality f of x is greater than 0. And then similarly, any x value that gives us an output that's below the x-axis solves the inequality f of x is less than 0. So to write a solution for each of these inequalities, we're determining what parts of the domain, in other words, what x values, what parts of the x-axis, correspond to outputs or y values that are either above or below the x-axis, depending on what we're looking for. So our first inequality is f of x is greater than or equal to 0. So we want to know which x values correspond to y values that are above or on the y-axis, or excuse me, the x-axis. They can be on the x-axis because we have f of x is equal to 0 as part of our inequality. So to the left of our first intercept, we're above. Then we dip down below. Once we get to -1, we come back above the x-axis. We dip down below again, and then after our last intercept, we're also above the x-axis. So we have 3 intervals of our domain that correspond to x values that have outputs above the x-axis. In other words, outputs that are positive. So everything from -infinity to -2, everything from -1 to 1, and then everything from 2 to infinity. And because we have equality as part of our inequality, we also include brackets around those specific endpoints. Of course, we never include brackets with infinity, but our actual numeric endpoints include brackets because we have equality as part of our inequality that we're solving. If we want to solve f of x is strictly greater than 0, the only difference is now we can't have equality. So we're not going to include our x-intercepts as potential solutions to this inequality. So we have the same intervals, but we now use parentheses instead of brackets to show that those endpoints, which happen to be on the x-axis, are not part of our solution. Next, f of x is less than or equal to 0. So now we want to know which x values give us outputs that are below the x-axis, which x values have y values that are less than 0. Again, because we have equality, we can include the intercepts as well. So everything between -2 and -1, and then everything between 1 and 2 corresponds to y values that are negative or below the x-axis. And again, we use brackets in this case because we have equality. If we take away the equal to part, we have the same intervals, and we change to parentheses to indicate that those endpoints are not included. So one thing I want you to notice about a problem like this is that whenever we're generating endpoints for intervals, notice all the endpoints correspond to x-intercepts. X-intercepts are significant because they represent the points where we change from positive to negative or from negative to positive in terms of the outputs of our function values. So intercepts represent key points. Everything revolves around the intercepts. Intercepts are where we're at 0. If we want things greater than 0 or things less than 0, these particular changes occur around our intercepts. So that's a big important thing to keep in mind when we're solving polynomial or rational inequalities. Now let's talk about what happens when we're not given a graph. So when a polynomial is given in function notation, in other words, we have f of x is equal to a rule corresponding to our function, our first step to solve an inequality is get everything on one side and 0 on the other side. So sometimes we have an inequality, in other words, we've got less than, greater than, less than or equal to, greater than or equal to, but we have things on different side of the inequality sign. So the polynomial is not all combined together. Part of it's on the left, part of it's on the right. If this is the case, then we need to make sure that everything is on one side. Typically, we like to put everything on the left-hand side just because we read left to right. So that's typically our consistent way of moving things around. So make sure everything's on one side and we have a 0 on the other side. That's our first step. Second step, solve the related equation f of x is equal to 0. This gives the corresponding x-intercepts. And as we decided with our graph, x-intercepts represent key points. These points represent the locations where the polynomial can change from positive to negative or vice versa. So if we're looking for particular values that correspond to outputs either greater than or less than 0, these are the key locations where we check the sign. Are we greater than? Are we less than? X-intercepts represent the endpoints for the intervals that we're going to write as part of our solution. The final step after we've determined our intercepts is to determine the intervals defined by the intercepts. In other words, what are all the values in between these intercepts? Break it down, take your entire domain, write it out, and split it up around these intercepts. And then in each of these intervals, pick a test value and check the outputs sign for that particular test value. So as we discussed before, one thing that's significant about intercepts is once we have our intercepts, we know that anything on either side or between our intercepts is either entirely above or entirely below the x-axis. So for any point we pick, the sign of that output corresponds to the sign of any output within that range of values. So if we pick a test value and the output for that test value is positive when we plug it into our function, that means that every single x value between those two intercepts in the particular interval we're talking about is going to have a positive output, which means that everything in that particular interval is always positive. Graphically speaking, that means it would always be above the x-axis. Same thing if we have a negative output. So we split up our number line, our domain, our x-axis, whatever you want to call it, among all these x-intercept values, and then we determine what's the behavior in each interval. And that's going to tell us which particular ranges in the interval notation domain we specifically want to keep as part of our solution to our inequality. Okay, let's try an example. So we want to solve 3 of x times x minus 1 is greater than 10 minus 2x. So our first step is get everything on one side and get 0 on the other side. So this is polynomial. We don't have any division by variables. We don't have any variables with fractional exponents, nothing like that. So this is polynomial, even though everything is split up and it's not all combined together. So we need to get everything on one side, simplify it, get a 0 on the other side. So first thing we need to do is just go ahead and distribute that 3x. It looks like factorization might help us in this case, but because we don't all have everything on one side of the equation, the factorization actually does not help us. It's not going to give us any extra information. So go ahead and distribute the 3x, and then we need to move over those two terms on the right-hand side. Again, it doesn't specifically matter which side we move to, but traditionally speaking, because we read left to right, it's helpful just to move everything to the left side. So we need to subtract the 10 and add the 2x. So if we do that, we're left with 3x squared minus x minus 10 is greater than 0. Next step is to solve the related equation. So now that we've gotten our polynomial on one side of the inequality sign, solve the related equation. And as we decided, this equation gives us our x-intercepts. It represents those key points where we flip from being positive to being negative or vice versa. This particular quadratic factors, but as we mentioned before, if it doesn't factor or if you don't want to try factoring, you can always use the quadratic formula to solve for x in a situation like this. So this factors as 3x plus 5 times x minus 2. Set each of these factors equal to 0 and solve for x. So the first factor gives us an x-intercept of negative 5/3, and the second factor gives us an x-intercept of 2. So what are we going to do with these? Well, here's our inequality. Here's our cleaned up inequality. Next step is to determine the intervals defined by the x-intercepts, and then pick a test value in each interval and check that particular input's sign using our function. So here's how we're going to split it up. Think of the horizontal line, what we're going to think of as a number line. Think of that like the x-axis. And so on this x-axis, we have two intercepts. We have an intercept at negative 5/3 and positive 2. So these are the locations where we are on the x-axis. So graphically speaking, what this means is that the graph on either side of these particular values is either entirely above or entirely below the x-axis. So our goal is to figure out which case are we in each one of these particular locations. Now what I like to go ahead and decide at this point is based on what kind of inequality do I have, am I going to include or am I going to exclude my endpoints as part of my solution? In other words, am I going to write them with parentheses or brackets? Well, because my inequality is just a greater than, there's no equal to part, I know that my endpoints are not going to be actually part of my solution. So I'm going to have to use parentheses. So I like to go ahead and indicate this by putting an open circle at each of these intercepts. That way when we get down to the end of the problem, we know we want to put parentheses around the intervals that we're going to include in our solution. So once we've determined that, we pick a test value, any test value we want in each of these intervals. The only numbers you cannot pick are the intercepts themselves, but otherwise you pick any number you want in each of these intervals and then plug it into your function. So I'm going to pick negative 4 on the left-hand side, 0 in between the two intercepts, and positive 4 on the right-hand side. Again, it doesn't matter what the numbers are as long as they're within the interval we're checking. Each of these test values I'm going to take and I'm now going to plug it into my inequality, specifically the form where everything was on one side and then there was a 0 on the other side. So think of it as taking an input and plugging it into your function and coming up with the output. So I plug in -4 to my polynomial. I simplify everything using order of operations, so we're left with 48 plus 4 minus 10, which simplifies down to 42. So in this particular interval, what I've now determined is that all the outputs for values that I come up with in this interval, all the inputs in this interval are going to correspond to positive outputs. Well, the inequality we're trying to solve is a greater than 0 inequality. We're looking specifically for x values that give me a positive output. That means that this interval, because my test value had a positive output, this interval is going to be included as part of my solution. So I'm just going to put a check mark there to show that I want to include this interval as part of my solution because it corresponds to y values outputs that are greater than 0, which are the ones we want. Now let's check the interval between the two intercepts. So I'm plugging in a test value of 0, plug it in, follow order of operations. Our output is -10. That means that any test value in this particular interval would give us a negative output. Because we only want intervals that have positive outputs, this particular interval is not going to be part of our solution. And last but not least, let's check 4. So plug in 4, follow order of operations, and we're left with an output of 34. So we found another interval where our outputs are going to be positive, so this interval is also going to be part of our solution. So the first and third intervals give us positive outputs. They accurately solve that inequality, 3x squared minus x minus 10 is greater than 0. But the second interval, the interval between the two intercepts, gives us negative outputs, so it does not correctly solve that inequality. So our solution is everything from -infinity to -5/3, and everything from 2 to infinity, but not including those endpoints because we don't have equality as part of our inequality. Let's try another one. So now we want to solve x minus 1 times x plus 3 times x plus 5 is less than or equal to 0. So our first step is to get everything on one side and 0 on the other side. Well, in this case, the step is already done for us. And in addition, it's fully factored. So as long as everything is on one side and 0 is on the other side, any factorization that's already done for us is only going to work in our favor. So step 1 is done. We can move on to step 2. Step 2 is to solve the related equation. So treat this as an equation instead of an inequality for the moment. So our related equation is x minus 1 times x plus 3 times x plus 5 is equal to 0. So we're solving for the x values that make this true. And as we mentioned, this is already factored, so most of the work has been done for us in this case. So set each of our factors equal to 0 and solve for the related x-intercept. So we get x is equal to 1, x is equal to -3, and x is equal to -5. These are going to be our 3 x-intercepts. So now we want to set up our intervals defined by the x-intercepts with endpoints. So we have -5, -3, and 1, and we have 4 intervals in this case split up by these 3 intercepts. Now before we pick a test value, let's determine, are we going to potentially include these endpoints as part of our solution? Well, our inequality has equal to, it has equality as part of the symbol, so that means we are going to include our endpoints when we write our intervals that give us our solution. So I'm going to put closed circles at these intervals, or excuse me, these intercepts, to show that I want to actually include these as part of my solution. Then I want to pick a test value in each interval. Pick something that's going to be easy to plug in. The easier numbers to plug in typically mean you're less likely to make a mistake, so pick something that's easy to plug in. So I'm going to pick a -6, a -4, 0, and 2. So let's start with -6. We're actually going to use a little bit of a shortcut here to check the sign. Keep in mind, we don't care what the actual value of any output is. We just care about the sign. We just want to know, in this case, what particular intervals correspond to outputs that are going to be less than or equal to 0. In other words, outputs that are going to be negative. So all I care about is what is the sign for the particular output I'm going to get. So because this is already factored, I'm going to kind of break this down and take a shortcut in order to determine our sign. So what I'm going to do is I'm going to check the sign for each of the individual factors, and then we're going to put it all together and figure out what would the sign be for the whole problem. So negative 6 minus 1 is negative. So I'm just going to indicate that this first factor would be negative based on this particular input. Negative 6 plus 3 is also negative. And then negative 6 plus 5 is negative as well. So let's think about what's happening. I'm taking three factors and multiplying them together. So if I were to fully simplify this, I end up multiplying three negative numbers together. Well, if we multiply an odd number of negatives, it leaves us with a negative output. So if we were to simplify this whole thing, come out with an actual output, whatever the number is, it's going to be a negative number. Now, because my inequality is a less than or equal to, the negative ranges are the ones I want. So that means this first interval is going to be part of my solution. All the outputs in this interval are going to be negative, so those particular x values in that interval correspond to part of my solution. Let's try the same thing with negative 4. So negative 4 minus 1 is going to be negative. Negative 4 plus 3 is also negative. But negative 4 plus 5 is positive. So now I have two negatives multiplied by a positive. Well, the two negatives together become positive. A positive times a positive is a positive. So this particular interval is not going to be part of our solution because the outputs in this interval are not less than 0. Now let's try an input of 0. 0 minus 1 is negative, 0 plus 3 is positive, and 0 plus 5 is also positive. So a negative times two positives in this case is going to be negative. So we're also going to include this particular range because we have negative outputs in this interval. Last but not least, let's check 2. 2 minus 1 is positive, 2 plus 3 is positive, and 2 plus 5 is also positive. Any number of positives multiplied always give us a positive output. So because our outputs are now greater than 0, they're positive numbers, we don't want to include this interval as part of our solution. So again, keeping in mind that because equality is part of our inequality, we write our solution set with the first and the third interval. So our solution is negative infinity to negative 5 and negative 3 to 1, including our endpoints. Let's try one more example. So we want to solve 2x minus 1 quantity squared is greater than negative 6. Okay, first step, get everything on one side and 0 on the other side. It's tempting to say this is already factored and it's going to be easy to work with. The problem is because we don't already have everything on one side, we've got the negative 6 on the right-hand side, this factorization isn't going to help us. So first step is just go ahead and redistribute everything before we actually start combining. So don't make the mistake of saying 2x minus 1 squared, I square the 2x, I square the negative 1, and I move on. Unfortunately, it's not that simple. Anytime we square a binomial, remember we have to FOIL it out. So it's not 2 multiplications, it's actually 4 multiplications. So 2x minus 1 squared is the same thing as 2x minus 1 times 2x minus 1. So multiply first, outer, inner, last, combine everything together, and you should get 4x squared minus 4x plus 1, still greater than negative 6. Now we can move our negative 6 over, so add it to both sides, and we're left with 4x squared minus 4x plus 7 is greater than 0. So now that everything is on one side, we solve the related equation. 4x squared minus 4x plus 7 is equal to 0. This particular polynomial, this particular quadratic, does not factor, so we need to use the quadratic formula to find our x-intercepts. So make sure you write the formula down before you start plugging in numbers. A is 4, B is negative 4, and C is 7. So plug in these numbers to our formula and simplify everything. What we really want to pay attention to is what's under the square root. So take a moment, simplify this. You should get a positive 4 plus or minus the square root of negative 96 divided by 8. So in terms of what this means for x-intercepts, it means we have a little bit of a problem. Because we're taking a square root of a negative, although we know how to deal with this, we know that it corresponds to something that's not a real number. Well, if when we solve for our x-intercepts, we end up with things that are not real numbers, means there are no x-intercepts in this case. So this is a quadratic that doesn't have any x-intercepts. So for our purposes, it means we fall under one of two cases. So think graphically back to when we looked at quadratics. The graphs are shaped like parabolas, they're shaped like U's. If we don't have any intercepts, it means either the graph is entirely above the x-axis, or possibly the graph is entirely below the x-axis. We don't actually touch or cross the x-axis anywhere on our graph. So how do we determine which case we're in? Well, we use the test value method again. The only difference is because we don't have any intercepts, we only have to check one test value. If the graph is entirely above or entirely below, then whatever sign for the output we get for any value we pick, the same sign is going to apply for every x value that we could plug in. So you can choose any test point you want. Typically, when in doubt, pick 0. 0 is the easiest number to plug in, and it usually results in the easiest algebra. You're less likely to make a mistake. So plug 0 into our function. Notice that the two terms at the front are going to go away, and we're just left with a positive 7. So that means that every single x value that we could plug into this particular function or this inequality is going to give us a positive output because our test value gave us a positive output. So in this case, because our inequality is a greater than inequality, we want all the x values that give us outputs that are positive. Our test value gave us a positive output. That means every value is going to give us a positive output. So our solution in this case is actually all real numbers. Any number we could plug into this particular quadratic function is going to correspond to a positive output, because if we were to graph this, our graph is entirely above the x-axis. Now, what if our test point had failed? If our test point had failed, that means that any test point would have failed. If you want to prove this to yourself, at least in this case, pick a couple other numbers and try plugging them in. If you do this, I guarantee you 100% you're going to come up with a positive output. So if we were in the opposite situation and we'd picked a test point and the test point would have failed, then again, any test point would have failed, which means, practically speaking, that we would have a no solution problem. So say instead our inequality had been 4x squared minus 4x plus 7 is less than 0. Well, in that case, because our graph is entirely above the x-axis, then there are no x values that correspond to an output that's less than 0. So if that had been our particular inequality, then we actually would have had no solution to this particular problem. Now let's look at rational inequalities. So if f of x is equal to p of x over q of x, where p of x and q of x are polynomials, this is a rational function, then a rational inequality is an inequality taking on one of four possible forms. F of x is less than 0, less than or equal to 0, greater than 0, or greater than or equal to 0. So essentially we're in the same situation as we were with our polynomial functions, except our function is now a ratio of two polynomials instead of just being a single polynomial. Now, most of the things we're going to do are going to be consistent from polynomial functions to rational functions. The only difference is that we have to take into account that the graphs of rational functions are a little bit interesting. Remember, we have vertical asymptotes in our graph, which correspond to breaks in our domain. So this is going to complicate things a little bit, but from a graphical standpoint, all we need to do is determine which intervals of the domain satisfy the particular inequality. However, as mentioned, we have to take into account that a rational function is undefined at its vertical asymptotes. In other words, at any point that corresponds to a vertical asymptote, we never include, in other words, never use brackets as part of that particular part of the solution. Any x value that corresponds to an x-intercept, we can use brackets with, because that actually corresponds to a point on the graph. But any x value that corresponds to a vertical asymptote, remember there is no point there. There's this imaginary break in the graph. So if we're going to include that x value as an endpoint for our particular solution, we have to make sure we use parentheses with that number instead of brackets. So let's look at an example. So here's our graph. This is a rational function, and we've graphed it and we have a vertical asymptote and one x-intercept. So our x-intercept is at x equals 1, and our single vertical asymptote is at x equals 2. So we want to solve our four inequalities. F of x is greater than or equal to 0, greater than 0, less than or equal to 0, and less than 0. So just like before, let's think about what this graph is telling us. So anything on the x-axis solves the equation f of x is equal to 0. Anything above the x-axis solves the inequality f of x is greater than 0. And anything below the x-axis solves the inequality f of x is less than 0. Now, one thing I want you to note here is we have a horizontal asymptote as well. So it's tempting to say that this particular line somehow splits our solutions into two parts. Do not make that mistake. All we care about is where are we in relation to the x-axis. So notice on the left-hand side of the graph, on the left-hand branch, we have a piece that's above the x-axis and a piece that's below. Even though that piece that's above is underneath our horizontal asymptote, it's still above the x-axis. So this particular piece on the left looks like it goes from negative infinity to positive 1. This is still above the x-axis, so it's still part of the inequality f of x is greater than 0, even though it's below our horizontal asymptote. So just make sure you pay attention to where the x-axis is versus where any horizontal asymptotes you may have are located. So f of x is greater than or equal to 0. So we want the intervals of the domain that give us outputs that are above or specifically on the x-axis. So as I just mentioned, we have everything from negative infinity to positive 1. That particular piece of our graph is above the x-axis, so that interval is going to be part of our solution. Now, because we have equality, we can include the number 1 as one of our endpoints. Because it's an intercept, there's an actual point there, we can use a bracket there. The right-hand branch of our graph is also above the x-axis, but how we write this interval is going to be a little different. So notice the endpoint for that particular branch, in terms of our x values, the endpoint is 2, but 2 corresponds to a vertical asymptote. There's no actual point there. So even though it's the dividing line between a negative portion of our graph and a positive portion of our graph, because there's no value there, there's no actual point there, we have to use parentheses. So in interval notation, the solution to our first inequality is everything from negative infinity to 1, including 1. 1 is included, there's a bracket there. And then everything from 2 to infinity, but not including 2, because 2 corresponds to a vertical asymptote. It's a division, it's a break in the graph, and there's no actual point there. If we get rid of equality, the only thing that changes is the x-intercepts are now not included. So anywhere there was a bracket, we now use parentheses. Notice nothing changed with the endpoint that corresponded to a vertical asymptote. It's not included with equality, it's not included without equality. If we want f of x is less than or equal to 0, that's going to be the range from 1 to 2. That's the only portion of the graph where we drop below the x-axis. So 1 corresponds to an intercept, 2 corresponds to a vertical asymptote. So we can include the endpoint at which we have an intercept. We can't include the endpoint at which we have a vertical asymptote. So it's the interval from 1 to 2, including 1, but not including 2. Again, intercept versus vertical asymptote, we include the first, we don't include the second. If we drop off equality, again, the only thing that changes is now we're not including the intercept. So same endpoints, but neither of our endpoints are included in this situation. So now let's talk about our algebraic situation. And the good news is most everything we did with the polynomial inequalities, algebraically speaking, are the same here. But we have to take into account that one additional consideration for asymptotes. So when our rational function is given in function notation, so f of x is equal to a polynomial divided by another polynomial, our first step to solve our rational inequality, just like with polynomial inequalities, is get everything on one side and get 0 on the other side. Now, because we have a rational function instead of a polynomial function, it may be a little more labor intensive to do this, but when we get to that, we'll deal with it. Just keep in mind everything's on one side, and also everything is combined into one rational expression, if at all possible. So everything's on one side, zero's on the other side, and the left-hand side of the inequality is one rational expression. Everything's fully simplified. Second step, we're actually going to solve two related equations. P of x is equal to 0 and Q of x is equal to 0. So separately, we're going to set the numerator and the denominator equal to 0 and solve two equations. The first equation gives us our x-intercepts. Anything that makes the numerator 0 makes the whole function 0, which corresponds, graphically speaking, to x-intercepts. Equation 2, when we set the denominator equal to 0, you may remember that gives us our vertical asymptotes. That gives us those places where we have an undefined value in the domain. So even though it's going to be an endpoint for our solution, it's not an included endpoint. So these points represent the possible locations where the polynomial could change from positive to negative or vice versa. However, again, we have to take into account that a rational function is undefined at its vertical asymptotes. So again, it's an endpoint, but it's not an included endpoint because there's no actual value there. It's the break in the graph. There are no points there. Finally, just like before, we want to determine the intervals defined by the x-intercepts, and in this case also the vertical asymptotes. And then we pick a test value and check its sign, just like we did before. Let's look at a basic example. So we want to solve 3 minus x divided by x plus 1 is less than or equal to 0. So first step, get everything on one side and get 0 on the other side. Make sure everything's combined into one rational expression. Well, that's been taken care of for us, so we don't have to do that. So immediately move to step 2. In this case, we're solving two equations. We set our numerator equal to 0 to find our intercepts, set our denominator equal to 0 to find our asymptotes. So 3 minus x is equal to 0, which means x is equal to 3. So we have a single x-intercept at x equals 3. And then for our vertical asymptotes, set our denominator equal to 0. So x is negative 1 is going to be our vertical asymptote. So make sure you keep in mind which one of these numbers is an intercept and which one of these numbers corresponds to an asymptote. Because what we do with the graph and what we do with our solution is going to vary depending on which situation we're in. Is it an intercept? Is it an asymptote? Okay, so set up our little diagram with our intercepts and our asymptotes. So we have negative 1, we have 3. Those are our key points. And then we're going to pick our test values like before. So let's go ahead and decide which one, if either of these, is going to be included and which one has to be excluded in terms of our endpoints. So our inequality has equality as part of it. So we can include an intercept, but again, we cannot include an asymptote. It doesn't matter what the inequality sign is, we never include an asymptote. So negative 1 was an asymptote, 3 was an intercept. So negative 1 is going to be excluded just because it's an asymptote, but because we had equality as part of our inequality, 3 can be included. It's an intercept. Now we pick our test values. So let's pick negative 2, 0, and 4 and check the signs. So just like before when we simplified things down a little bit, let's do that here. So as opposed to having to come up with the actual outputs, again, all we really care about is the sign. So let's just see if we can simplify things to figure out what the sign would be in each interval. So 3 minus negative 2, well, that's going to be positive. So our numerator is positive. Negative 2 plus 1 is negative. So we have a positive divided by a negative. Well, anytime we're dividing two opposite signs, the output is going to be negative. We want particular ranges of values that give us negative outputs, that give us outputs less than or equal to 0. So that means this first interval is included as part of our solution. Now let's check 0. So 3 minus 0 is positive. 0 plus 1 is also positive. So this is a positive divided by a positive, which also gives us a positive output. Because we want less than 0 outputs, this is not part of our solution. 3 minus 4 is negative. 4 plus 1 is positive. So negative divided by positive, dividing opposite signs. So this is a negative output. So again, we're going to keep this interval as part of our solution. So now we write our solution, keeping in mind which input is included, which endpoint is not included. So we have everything from negative infinity to negative 1, not including -1, remember that was a vertical asymptote, and then everything from 3 to infinity, including 3, because there was equality and because 3 corresponded to an x-intercept. Let's try another example. So we want to solve 4x minus 5 divided by x minus 2 is less than 3. First step is get everything on one side and get 0 on the other side and fully simplify the side with the rational expression. So I need to move the 3 over first. So I'm just subtracting the 3. Don't make the mistake of trying to multiply or divide anything here. The only way to get a 0 on one side is to add or subtract whatever's on that side that we want to get the 0 on. So subtract our 3. Now we need to simplify everything down. So in order to find x-intercepts and find vertical asymptotes, we have to have a single numerator and a single denominator. Well, in this case, because the 3 is subtracted and it's not subtracted as part of the rational expression, we have to use algebra to combine it. So it's one numerator and one denominator. Well, if I have something that has a denominator and something that doesn't, I know I need to get a common denominator first before I can combine anything. If my only denominator is x minus 2, then that's going to be the denominator I need for that other term that's being subtracted in this case. So I'm going to multiply top and bottom by x minus 2. So that becomes 3 times x minus 2 divided by x minus 2. We can do this because x minus 2 over x minus 2, that's really just 1. So I'm really just multiplying by 1 in kind of a strange looking way. Now I need to distribute, so distribute that 3. And then we want to combine our numerators together. And of course, whenever we're adding or subtracting anything with the denominator stays the same, and we just combine our numerators. So make sure when you combine, you take into account that we're subtracting. So everything in the second numerator has to be subtracted. Make sure that it's completely subtracted because this is potentially going to flip a couple signs when we combine. Once we combine everything together, we have 4x minus 3x. And -5 minus a -6, so that's going to change into addition. So our numerator becomes x plus 1, and then our denominator is still x minus 2. So our fully simplified inequality is x plus 1 divided by x minus 2 is less than 0. Now I solve my related equations. So to find my x-intercepts, I set my numerator equal to 0 and solve. So x equals -1 is going to be my x-intercept for this particular function. And then I set my denominator equal to 0 for my vertical asymptotes, and I solve for x equals 2, so that's going to be my single vertical asymptote. Now I need to set up my test values, set up my x-axis. I have a -1 and a +2 as my key points. And if you remember, +2 is an asymptote, -1 is an intercept. So my inequality I'm solving is a less than. There is no equality as part of the inequality. So in this case, it means that neither of the endpoints are going to be included. Regardless of whether it corresponds to an asymptote or an x-intercept, neither endpoint is included because equality is not part of my particular inequality that I'm solving. Pick our test values. So let's pick -2, 0, and 3. And again, let's take the shortcut. Let's just figure out what the sign for the numerator and denominator is going to be. So -2 plus 1 is going to be negative. -2 minus 2 is also negative. So negative over negative combines to give us a positive. Because we're solving a less than inequality, that means this first interval is not part of our solution. Now let's try 0. 0 plus 1 is positive. 0 minus 2 is negative. So we have a positive divided by a negative. Dividing opposite signs means our output is negative. Because we're solving a less than, this is part of our solution. And then 3 plus 1 is positive. 3 minus 2 is also positive. So positive divided by positive gives us a positive output. So this particular interval is not included. So our solution is everything from -1 to +2, not including those endpoints because equality was not part of our inequality. Let's try one final example. We want to solve 1 divided by x minus 2 is greater than or equal to 1 divided by x plus 3. So our first step is to get everything on one side and get a 0 on the other side. Now, algebraically speaking, This one is a little interesting. So immediately, based on math you've seen before, intuition may say cross multiply. That's typically a good option for when we have two rational expressions and we want to combine things together, maybe solve for a variable. But let's think about what would happen if we tried to cross multiply. So say we want to move everything on the left over to the right, and maybe we want to do that by cross multiplying by x plus 3. The problem with trying something like that is, how do we know what sign x plus 3 is? So if you remember, one thing that's unique about inequalities is if we're multiplying or dividing by a negative, we have to flip the inequality sign. Well, depending on the value of x plus 3 could be positive, or x plus 3 could be negative. Unfortunately, without any additional information about x, we don't know which situation we're in, and depending on how x varies, we're in one situation versus the other. So multiplying by x plus 3 is not a good option because we don't know what to do with the inequality sign. Ultimately, our problem with cross multiplication is this is not an equation, it's an inequality. The rule for cross multiplication, unfortunately, does not apply in an inequality scenario. So we have to use the technique we've used before. We have to take whatever we want to move over and just add it or subtract it. So in this case, it looks like subtracting an entire rational expression, which is okay. We take it as one unit, subtract it, move it over to the other side. So we now have 1 over x minus 2 minus 1 over x plus 3 is greater than or equal to 0. So we've got the 0, and now we want to combine everything on the left-hand side so that we have one rational expression. So in this case, we have two denominators. Neither denominator has anything in common with the other one. So that means to get a common denominator, we have to have both of these denominators as factors. So whatever factor that particular rational expression is missing, that's what we're going to multiply by. So our first rational expression, in order to get our common denominator, would need an x plus 3. So I need to multiply by an x plus 3. My second denominator needs an x minus 2, so I have to multiply that rational expression by x minus 2. So I'm left with this particular combination of rational expressions. Again, for the first one, I added on the x plus 3. For the second one, I added on the x minus 2. And notice now the two denominators are the same. They have factors in different order, but they're essentially the same. So now I need to combine my numerators, again paying attention to the fact that I'm subtracting the second rational expression. So everything in parentheses in the second numerator has to be subtracted. So x plus 3 minus x minus 2 combined into one numerator. Notice the x's are going to cancel in this case, so I'm just left with 3 minus a negative 2, which is going to give me a positive 5. So my final rational expression is going to be 5 over x minus 2 times x plus 3 is greater than or equal to 0. Now I'm going to leave the denominator factored. We know we're going to have to solve an equation where we set the denominator equal to 0. Ultimately, we would have to factor anyway. So if it's already done for us, just leave it alone. Leave it in the form it's in. Now we're going to solve our related equations. Set my numerator and my denominator equal to 0. So to find x-intercepts, we set the numerator equal to 0. Okay, so we get the equation 5 equals 0. Notice there's no x, there's nothing to solve for, and this is not a true equation. That means there are no x-intercepts for this particular graph. It means it's entirely above or entirely below for different pieces of the graph. So there are no x-intercepts for this graph. For vertical asymptotes, we set our denominator equal to 0. In this case, we have two factors equal to 0. So we get x is positive 2 and x is negative 3. So if we were to graph this rational expression, it has two vertical asymptotes. So now let's put this on our chart. Again, specifically referring to our particular form of our inequality where we have a 0 and then everything's combined on the left-hand side. So we have two key points, one at negative 3, one at positive 2. And as we decided, both of these correspond to vertical asymptotes. So let's see whether or not these are going to be included. Well, our inequality symbol is greater than or equal to, so equality is part of our problem. Normally we can include our endpoints. However, because these endpoints both correspond to asymptotes, we know there's no actual point there. There's a break in the graph and there are no values at -3 or 2. So even though equality is part of this inequality, we're not going to include the endpoints because they're both vertical asymptotes. So when we write our solution, any intervals we want to include are going to have parentheses around them. Pick a test value, so let's do -4, 0, and 3. So for our first range, notice we're not plugging anything into the numerator. So the sign of the numerator is never going to change. Because the numerator is identically 5, each numerator is always going to be positive. So what we're really wanting to pay attention to is what are the signs for the two factors in the denominator. So our numerator is positive, and then the first factor in the denominator is negative. The second one is also negative. So we have a positive divided by two negatives. So the two negatives in the denominator multiply to give me a positive. So I have a positive over a positive, which is also positive. I want everything that gives me an output that's greater than or equal to 0. So because this particular interval corresponds to positive outputs, I'm going to keep this interval as part of my solution. Now let's check 0. So 5 is always positive again. 0 minus 2 is negative. 0 plus 3 is positive. So we have a positive divided by a negative times a positive. So the denominator becomes negative. The numerator stays positive. Dividing two opposite signs gives me a negative, which means this interval is not included as part of my solution. And then with 3, 3 minus 2 is positive. 3 plus 3 is also positive. So we have a positive divided by two positives, which gives us a positive output, which means this interval is also part of our solution. So our solution is -infinity to -3 and 2 to infinity, not including those endpoints, not necessarily because of the form of our inequality, but because both of these both of these endpoints correspond to vertical asymptotes. To summarize, polynomial and rational inequalities result from adding an inequality sign of any of the four forms to a polynomial or rational expression. In other words, we take what we've seen before, what we've talked about in this unit with polynomial functions and rational functions, and normally where we'd solve our equation that solves for our intercepts, where we set our function equal to 0, now we're putting an inequality sign in place of the equality sign. So to solve any type of inequality of this form, our first step is to get everything on one side of the inequality sign fully simplified and get a 0 on the other side. Our second step is to solve for the corresponding x-intercepts, and in the case of rational inequalities, solve for vertical asymptotes. So depending on our situation, our endpoints of these forms may or may not be included. Equality allows us to include x-intercepts, but not vertical asymptotes. And then complete inequality doesn't allow us to include either endpoint as part of our solution. Our final step after we solve for these key points is to set up intervals around these key points and check for the sign of a test value in each interval. Intervals with the sign we want, in other words, if we're less than 0, we're looking for negative outputs. If we're greater than 0, we're looking for positive outputs. Intervals with the desired sign are part of the solution, and then intervals with the opposite sign are not part of our solution.